Do you remember what I said at the end of previous lecture? I said that these two time complexities are pretty much the same. Now, obviously they are different, but as far as big O notation is concerned, these are the same. So, what big O notation is? Well, do you think that this plus 2 is important? Imagine that n is a billion, so you pretty much don't care whether you need to do a billion operations or billion plus 2, right? So what big O notation does is it kind of hides the unimportant and leaves the important. Because if we ignore the unimportant, that means this plus 2 and times 3, we get the important, and this is how we get big O notation from time complexity. So let's take a look at the definition. F of x is in the big O of G if and only if there exists key and x0, such as that for all x greater than or equal to x0, the f of x is less or equal to k times g of x. So you can think of big O of n as a big box that contains all the algorithms that have linear time complexity. So, for example, this algorithm that takes an array, and if the size of array is greater than 50, it returns true, else it returns false. Pretty simple, right? What will be the time complexity of this algorithm? You can pause the video and try to figure it out. So, the precise time complexity would be 2, right? Because we need to check for length and either return true or return false. So what can we figure out from this? Well, it doesn't matter how big the input is, this algorithm would still have constant time complexity. And in big O notation, all the constant algorithms are in this class, or box if you want, and it is the smallest box possible. You cannot get algorithm that is faster than big O of 1. Now, let's take a look at this algorithm. What big O box it will fit into? Well, first of all, let me compute the actual time complexity, and then we can move on to big O. So, we have here two operations before the first cycle. Then, in the first cycle, we go from 0 to n. And what do? Well, we check whether the number on index I is smaller or equal to 10. If it is, we add this number to result variable. And then there is this inner cycle. And this one loops once again from 0 to n. And it basically prints every number in array. Feel free to pause the video and compute the time complexity on your own. So, I will start with the inner cycle. So, initializing to 0, that is one instruction. Then for each element, we check whether j is smaller than n. Then we increment j and print element on index j. So this inner cycle will have time complexity of 3n plus 1, okay? Now, let's take a look at the rest. At the beginning, there is the initialization of result variable. And also, we initialize I to 0. So let's write plus 2. Then for each element, so n times, I check whether the array on index I is smaller than 10. But I don't know whether this is true or not, right? It depends on what elements are in array. For example, if all the numbers in array are greater than 10, we need just one instruction, because this line will never happen. But if all the numbers are smaller than 10, we need 3 instructions because of the plus and assignment operation. So what do? Well, we need to count with the worst case scenario, because we want to know the complexity of worst case. Okay, so we get 3n plus n times the complexity of this for loop, and we computed the complexity of this inner loop before, and it was 3n plus 1. And by multiplying it, we get the final time complexity, and that is 3n squared plus 4n, because by multiplying we get n, and we already have 3n, and plus 2. This is the time complexity of this algorithm. So, what is the big O complexity of this? We can get the big O complexity by just taking the biggest term. So, in this case, it will be 3n squared. Because if, for example, n is a billion, we get 3 times billion times billion. And that is greater than 4 billion, right? So 3n squared is the largest term. Now all we need to do is get rid of the constant and we get our big O complexity. So this algorithm has time complexity of big O of n squared. And this approach works for every time complexity. For example, if I take the time complexity from previous case, the big O complexity will be the largest term from this expression, and that is just 3n without the constant in front of it, and that is just n. So we get big O of n, and that is pretty much it for this video. If you have any questions, feel free to ask, and I will see you next time.